Hi all, welcome back to the session on power electronics. So we were discussing about the module 1, that is the thyristors, and so far we have discussed the static anode cathode characteristics of a thyristor. In today's session we will discuss about the gate characteristics of a thyristor. So here gate plays an important role in case of a thyristor. We already have discussed that when we are going to apply the gate cathode voltage, that allows the triggering of the thyristors. Okay, and the thyristor from the non-conducting state moves back to the conducting state. So now let us see the gate characteristics. Gate characteristics means, let us plot, that is how we have studied the static anode cathode characteristics for current flowing versus the voltage applied. Similarly here also, let us consider the gate voltage versus the current flowing in the circuit, gate circuit. Why we need to know these characteristics is, we are going to supply the pulses to turn on the thyristor. So whatever the pulses, the desired or assured firing, are we able to give the assured firing to the thyristor? For that you should know why the gate characteristics. Then now the maximum dissipation of power. So how the power loss and what duration of the time if we are going to give the gate pulse, then what will be the loss of power that is permissible by the gate. So that to discuss that, we are going to study the gate characteristics of a thyristor. So let us say that we have gate current versus the gate voltage. So we are going to draw the graph in such a way that, now let us assume that the temperature is a maximum temperature, you are giving the temperature maximum. So when the temperature is maximum, what happens? When a small gate voltage is applied, then the current starts rising to its maximum. So let us consider, for a maximum temperature, this is the curve that we are going to apply. So this is nothing but maximum temperature. When the maximum temperature is applied across the P and N. Now if you see here, that is already discussed about the 4 layers of a thyristor. This is the 4 layers of the thyristor: anode, cathode and the gate other terminals. So this gate characteristics is determined when we are going to apply the gate voltage. So one single P and one single N region is included. Hence the characteristic of a gate is similar to that of a diode, which we have already studied. Okay. So here across this one single junction, we are going to apply the gate cathode voltage. So when the temperature is maximum, then what happens? For a small value of voltage itself, you are going to get a maximum current. So this is known as the maximum temperature curve. Okay, the spreading of the curve is in such a manner. Similarly, if the temperature is minimum, when the temperature is minimum, what happens? We have to give a high voltage in order to reach the maximum value of current. So to reach this maximum value of current, you need to give a greater value of voltage. So let us consider this curve. The spreading of this curve is due to the minimum temperature. Okay. Now once we have the value of voltage and current across the gate circuit, we can also write the dissipation of power. So once the current is maximum, here with respect to the voltage applied is maximum with respect to the minimum temperature, then we can say that the maximum power loss can take place within this region. So this curve is nothing but the maximum So this curve is nothing but the maximum power dissipation curve. Means above this, if you are going to have any power loss, then it is going to damage the thyristor. So whatever power loss that you are going to get should be within this limit. But should be within this limit means there should be again another minimum power dissipation curve, within which you have to apply the power or the signal, gate characteristic signal. Okay. So, let us say that this is the minimum power, gate power, that is going to be Pg represents the gate power. So, this curve again represents the minimum gate power that is applied. So, whenever we speak about the gate characteristics, the characteristics should lie between the maximum power dissipation to the minimum power dissipation. Now, corresponding, now this is a maximum power dissipation curve, corresponding value of current will be the maximum Ig maximum gate current. Similarly, here when we draw the tangent towards this line, what are the corresponding voltage will be the Vg maximum. So, these are the maximum and maximum voltage and maximum current that we are going to come across, the limits that can be applied. So, with respect to the minimum power curve, so here Vg minimum gate voltage, similarly here minimum gate current. So, within this range, whenever we are using the gate to turn on the thyristors, we need to provide sufficient amount of current ranging from the values Ig minimum to Ig maximum. Similarly, the required voltage that you are going to apply across the gate cathode terminal should be within this range Vg maximum to Vg minimum. Only if this is satisfied. Now, you can see that this is a region of operation, that is safe operating region. Okay. Only with if your values that you are going to apply between the VGS terminal, that is across the gate to cathode, and the current flowing is within this range, only then successful turn on of the thyristor can take place. So, these are the permissible limits of the thyristors, that is gates, current as well as the voltage. Now, up to this point, okay, let us say OA point, up to this point, whatever devices, OA is the region where whatever the voltage you are going to apply, it will never turn on any of the thyristor. Okay. So, whatever the voltage we are going to apply across this Vg minimum to Ig minimum, let us call it as OL, OV. So, the points OL and OV are the points on the curve during which the minimum voltage and minimum current is required. Okay. So, only at this point the triggering may happen. Okay. But after this point, whenever you are going to use, so after these points Vg minimum and Ig minimum, whatever the points you are going to give or what are the voltage or current you are going to apply will help for the successful turning on of the thyristor. So, this is a safe operating point, and Vg max to Ig max, let us say the points OP and the points OQ are the maximum values that can be applied across the gate terminal. If you apply any point more than this, then the thyristor will go to the damaging state. So, this is the safe operating area. Now, when we speak about safe operating area, another point comes into picture like the quiescent point, the load line concept. So, here when we are applying the load line concept, how do we say that we can apply the load line? The load line is applied to find out the characteristics of V and I. Okay, like say for example, same as that of the load line for a diode, here also a gate characteristic is nothing but a PN junction. So, this also resembles a diode. So, the load line concept as we are going to study for a diode, here also it is the same. Now, let us consider or let us apply a KVL equation just to know which are the operating points on the load line. Let us consider this simple circuit here, that is a gate characteristic circuit, where if we apply the KCL we will get VGS is equal to sum of EMF is equal to sum of IR products. So, IG is the current flowing here, IG into RG plus VG. VG is the gate voltage, the actual gate voltage we are applying across the gate to cathode region. Okay. So, now how we are going to find out the points, operating points, or how we are going to apply the concept of load line is, now we know that VG and IG are the terminals given. So, at one point at IG is equal to 0. When you apply IG is equal to 0, what happens? VGS is equal to VG. So, whatever the source, gate to source voltage you are applying will be the same voltage across the point VG. So, here across this curve VG is this is VG maximum. So, here let us consider somewhere here we have got the point VG. Okay. This is for the load line. Let us consider the point to be a point known as H. Now, similarly, one point of the load line we have found out. We have to find out the characteristics between the voltage and current, that is the load line concept. So, here when we are going to apply VG is equal to 0. Now, when this is 0, what will happen? You have to find out what is the gate current IG. So, IG is equal to VGS divided by RG. So, VGS divided by RG will somewhere come around here. Let us call this point as HD. So, now what we have to do? We have to draw a line, that is a load line. I hope you have understood how to find out the points for a load line. Now, for a gate characteristics, since it is a diode, it resembles as a diode, as a PN junction. So, we are applying the concepts of the load line concepts of a diode. Now, what we have to do? We have found out the 2 points for drawing the load line. So, now we will draw the load line from H to D. Okay. Now, which are the best operating points? Okay, let us say somewhere here in middle, S is the perfect point where the thyristor can be turned on by applying the gate characteristics. The maximum and minimum permissible is S1 and S2. Above S1, the operating point, that is a quiescent point S1 is the maximum limit. Below this S2, this is the maximum limit. So, when you are applying the operating point, in order to find out best operating points, S1 and S2 are the maximum and minimum limits of an operating point, and S is said to be the perfect point. So, it is also known as a quiescent point. So, this is how we are going to find out the load line concept, which is the best operating point. Now, if you are giving the voltage and current across this gate terminal in such a way that it is satisfying this, so there will be a perfect turn on of the thyristor. Okay, and within the duration, within the allotted duration of time. Now, similarly, we have to find out what are the maximum and what are the minimum resistance. You have found out what is the gate current, you have found out what is the gate voltage, gate current, gate voltage. Now, you should find out what is the condition where the maximum resistance or the minimum resistance what you are choosing is sufficient, or is it allowing the device, the current to flow through the thyristor. Okay. So, let us draw a tangential line across this maximum power curve. Okay. So, this point H, E, this point HE where you have the value of Rg, maximum value of Rg, and similarly here at this point F. So, this is the Rg minimum point. Okay. So, Rg minimum, Rg maximum. Within this point Rg minimum and Rg maximum, this is the range at which this resistance can be chosen. Okay. So, Ig, Vg and Rg, with all these 3 parameters, we can ensure a successful firing of the thyristor by applying the gate pulse. So, this is the general characteristics of a gate circuit for a thyristor. Also know that with the sufficient gate current applied across the gate to cathode terminal, only then the thyristor goes on. Now, let us say that the duration of pulse, this is the on time duration, that is T, and T1 is the total time period of the pulse that we are going to apply across the gate to cathode. Now, we want to find out what is the maximum power dissipated. So, we know that the maximum power dissipated is because of the current flowing Ig and because of the voltage supplied Vg. So, Vg into Ig will give the maximum gate power applied. Okay. So, it can also be taken as for one instant, for one time interval, that is Pg average divided by the pulse duration T. So, now here the frequency F1 by T1 is given as T is the total time, T1 is the total time period. So, frequency of firing is nothing but 1 by T1. So, T is the pulse width. So, this is the value of the pulse width. Now, we also know that duty cycle is defined as on time divided by the total time period of the device. So, here the total time period of the device is nothing but T1, on time is T. So, T by T1 is nothing but duty cycle del. So, that is also given by 1 by T1 is nothing but the frequency of firing pulse. So, we can also rewrite the duty cycle as F into T. Okay, substituting that in the given equation, the Pg average value will be equal to delta, that is we are going to replace it, that is less than or equal to the maximum value of the gate pulse applied. So, using this equation we will be calculating while solving problems, we will be making use of this equation and finding out how we are going to vary the value, and for the given gate power loss will the thyristor go to the on state. Okay. So, turn on methods of a thyristor is we can turn on the thyristor in different methods. Okay. The main intention is we already know that there will be 3 junctions J1, J2 and J3. So, out of these 3 junctions, by applying the positive or the forward bias condition across anode and cathode, automatically J1 and J3 goes on. What is the main challenging part is you have to break this junction J2 in order for the current to flow completely from anode to cathode. Only in this state the thyristor is known to be in its on state. Okay, so there are different methods by which you can turn on the thyristor. So, the first method is forward voltage triggering. Forward voltage triggering means now we have the 4 different layers. Now, without the application of gate, what we are going to do? We are going to give a high value of forward anode to cathode voltage. So, what will happen? J1 and J2 are already forward bias, J1 and J3 are already forward biased. J2, by applying more positive potential here, what happens? The holes whatever is created in the P region is forcefully moved to this side, and the N region which is in excess of electrons moves towards the other part because of the repulsion force. So, what happens? Because of this high voltage across anode and cathode, this junction J2 is also in the forward bias condition. By applying this high voltage method, you can turn on the thyristor. That is one method. Okay. Similarly, the thermal triggering. Thermal means increasing the temperature. Now, we know that we have already studied the basics of diodes and transistors. Always within a junction, we speak with respect to the junction capacitance. Now, if you are going to increase the junction, means at each junction, junction capacitance means at each junction between a P and N region, it will act as a junction capacitor, and if we are going, or there will be, if we are going to apply some temperature, some heat to it, what happens? It will allow the flow of charges. Okay. Similarly, now in this case, the junction capacitance across the J2 junction, if you are going to increase the temperature at the junction, okay, the junction temperature of J2, if it is increased, it has a chance of turning on the thyristor. Means this J2 will be in its forward bias condition. We also know that whenever the temperature increases, there will be free movement of electrons. The movement is much easier and hence the current can flow from anode to cathode terminal. Okay, so this is another method of turning on by increasing the heat across the junction J2. Okay. Next is the radiation triggering or light triggering. So now first we have to need to understand what is this isolation. Isolation means, now we already know that anode to cathode, whatever the voltage we are going to apply is a high voltage. But the gate to cathode, whatever the voltage we are applying is a very small voltage. Okay. And it is only used for the controlling, turning on and turning off, only the controlling part. So this part of the circuit, the gate to cathode part, whatever the power supply or the device, the element, the components what you are going to use, that forms a control circuit. Okay. Similarly, anode to cathode, whatever the voltage you are going to apply is always a high voltage, and this part and the other equipments, the load, the motors, whatever the other equipments you are connecting with this will always be of a high power, hence it is known as the power circuit. So this gate to cathode is known as the control circuit, anode to cathode is known as the power circuit. Okay. So what we need to do now? We need to isolate power and control circuit. Why? High power, here all the low power equipments you are using, once if the power flows into the gate, then all the components that is connected in the gate circuit will be damaged. So in order to avoid that, safeguard the components that you are using in the control circuit, we need to isolate power circuit and control circuit. Now when this triggering, turning on comes into picture, we need to take care about this, because we are doing the method of gate triggering and we say that this is the best method we follow to turn on a thyristor. Now when we are using this gate turn on method, then what we should do? We should take care such that there is no high current flowing into the gate circuit. In order to achieve that, we need to provide isolation. You can use opto isolators, optocouplers, transformers, and you can isolate, that is from the primary side to the secondary side, you can isolate the circuit. Okay. Later in detail we will go when we speak about in the next sessions. So now the first method is DC gate triggering. So DC gate triggering means we are going to apply a DC pulse, a constant continuous signal is applied with some amplitude. Let us say A. Okay. Now depending on what is the requirement of the gate pulse, gate signal, we are going to apply that level of voltage. So this method can be used. But what about the isolation? In case of DC supply, we cannot use, we don't have any isolation circuitries as such. Okay. So in case of a DC signal, when we are applying the DC signal, we cannot provide isolation. Since we cannot provide isolation, okay, and one more thing is a continuous signal you are going to give across the gate terminal. But what we require, only some small portion of the gate is sufficient to turn it on. After that, whether whatever you do with the gate, it does not have any effect on the layers. Okay. So here only for some duration of time the gate is sufficient. But what happens in a DC signal? Continuously there will be a gate signal. Okay. So this type, this method of DC gate triggering, we cannot provide isolation and continuous gate signal we are going to supply, which in turn causes power loss. So we don't go with this method of gate triggering. Next, coming to AC gate triggering. We know that AC means alternating circuit. Let us say that a symmetrical waveform is applied, positive, negative, n number of cycles is applied across the gate to cathode circuitry. And what happens here? Because we have an AC as a signal, AC we can use transformers, easily isolation can be provided here. Yes, but what happens? continuously you are giving positive, negative, for which we require only for one instant we require the gate signal. After that we do not need of any signal input to the gate and cathode. Then what happens here also, there will be loss of signal, power loss. Okay. So, this method can be adopted, but what we will be ending up in more power loss. Okay. Next, coming to pulse triggering, pulse gate triggering method. In case of pulse gate triggering method, what we can do is only at some instant of time, for every 10 seconds you are releasing one pulse. Like that we can design the circuit using only for that instant of time you can provide the gate pulses. Okay. And what about the isolation here? In case of isolation, you can use a pulse transformer, 1:1 isolation transformer or pulse transformer, which isolates power circuit and the control circuit. So, in case of pulse gate triggering method, you are isolating power circuit and control circuit, as well as you are going to provide only small pulses of small duration. So that what happens? The power loss is also reduced. So, out of these three, DC, AC and pulse, the best preferred method of triggering is the pulse gate triggering method. Next is the different firing circuits of an SCR. So, we are already just now we saw that by using any one of the method we can turn on, and out of the many available methods we prefer gate triggering method. And out of gate triggering methods, out of DC, AC and pulse, we prefer pulse triggering method. And when we prefer pulse triggering method, we already discussed that we can use a pulse isolation transformer or an optocoupler, opto-isolator for circuiting, for splitting power circuit and a control circuit. Okay. Now, whatever the firing means the signal that we require to turn on the SCR. So, the firing circuits whatever we are going to design, now it should be of these conditions must be satisfied. That is, it should be of adequate amplitude. The pulse what you are going to generate out of the different elements available, it should be of adequate amplitude, it should be of a short rise time and duration. And the duration means the instant at which the SCR has to go, little bit you can go plus or minus the instant of time where it is going to turn on. So, this duration also must be specific such that there should not be excess of power loss taking place in the device or the circuit. And it should also, we have to consider that whenever the main circuit, whenever the power circuit says that the thyristor is favorable for turning on, only at that instant of time we need to supply the firing pulses. Okay, only when the main circuit is ready and waiting for the signal from the gate to turn on, only then we have to turn on the signal. So, keeping all these three main concepts in mind, we have to design the firing circuits. Now, depending on what is the main type of elements we are going to use in the circuit, we have three different types of firing circuits. We have many more types. Now, for the syllabus we have to study three different types of turning on methods, that is depending on the types of firing elements what we are using in a circuit. First type is the R firing circuit or resistance firing circuit. Second is resistance capacitance firing circuit and UJT firing circuit. Now, using these different devices, now in the circuit you are using only the resistors, that circuit is known as a resistance firing circuit, means by using the resistors we are going to generate the pulses that satisfies these three conditions. Similarly, resistance capacitance combination we are going to use and we are going to check whether it satisfies all the three conditions and whether it is going to be suitable for turning on the thyristor. Similarly, Uni Junction Transistors. So, depending on that small transistor what we are going to use here, we are going to generate the pulses. Usually, R and RC triggering is used for the AC type signal where we are going to generate the pulses. UJT is used for either you can use it with the microprocessor or any type of digital instruments, and it usually used for a DC type of signal input. Now we will see in detail about the resistance triggering circuit. In case of resistance triggering circuit, we have the thyristor. To the thyristor, that is the gate circuit, we are going to use a resistance. So here R1 resistance is the current limiting resistor. It limits the current flowing into the circuit, and R2 is the variable resistor. In order to increase or decrease the value of current flowing into the circuit, we are going to use the R2 resistor. It is nothing but a variable resistor, and here we are going to use a diode D. See the direction of the diode, it allows only positive voltage to flow through it positively, okay, such that for the gate, whenever you are applying the signals across the gate pulse, that gate signal should not be a negative signal. To ensure that, we always use a diode in this direction such that it allows only the positive pulses to be supplied here. Okay. Next, R is the stabilizing resistor. You are going to give the input across gate to cathode, that is the input voltage that we are going to apply. In order to stabilize the applied voltage here, we are going to use R. This resistor, it is also known as the stabilizing resistor. Okay, so these are the functions of the different resistors which we are going to use. Now let us see how the operation takes place. Now only when the switch, thyristor is a switch, only when the switch is closed, only it allows the path for the flow of current, and hence source is connected to the load via the switch and the current flows completely in a circuit. Okay. Similarly, in case, that is when this load current has to be connected and you have to get some output, let us consider a minimum value, that is this R2 is a variable one. Now let us consider the value of R2 is very high. We know that when the value of the resistor is very high, what happens to the flow of current? We know current and R are inversely proportional. If you increase the current, the resistance will be reduced. Now we have increased the resistance R2. So what will happen to the flow of current I? It is going to be very small. Now let us come to the circuit here, the waveforms. Now, considering the condition when the value of R2 is large, input is a sinusoidal signal. So we are taking the input as a sinusoidal signal here. Now we know that for every gate signal, for every thyristor, they will have specified what is the threshold value of the gate voltage, what should be the minimum value, what should be the current minimum, voltage minimum, maximum power dissipation, all these specifications will be specified. Similarly, what should be the threshold voltage you have to apply in order to turn on the gate, turn on the SCR by using gate will also be specified. Let us assume that we have the threshold, the gate threshold voltage to be some value VGT here. Now when the current, the value of the R2 is very large, what happens? Small current flows. So small current flows means you are going to get a small peak here. Okay, that is a voltage across gate to cathode. So when this voltage across gate to cathode is very small, the peak value of it is not touching the threshold value itself. When it is not touching the threshold value, then what happens? The gate pulse is not touching the threshold value, there is no possibility of turning on of the thyristor. Okay. Now what will happen when it is not turned on? Then what will happen? Thyristor is still in the off state. Once it is in the off state, source is not connected to load. So what happens? No output voltage. Okay, across the thyristor. If you do not have any output voltage, then what happens? Whatever the input you have, the same will be available at the output of the thyristor. Okay, this is the first case when R2 is large. Similarly, next we will come to the next point. We are going to vary this value. We are going to keep this R2 to be a minimum, optimum value. So when this value of R2 is in the optimum value, then what happens? Some amount of current is going to flow in such a way that this peak, the voltage across the gate to cathode, whatever is generated, this peak value, the peak value is going to exactly touch the threshold value. So, at this point when the gate pulse, whatever the elements you are using here and generating the pulses, gate pulses, that is exactly going to touch the threshold value, that is the given gate's threshold value. So, what will happen at this instant of time only, the switch, the thyristor is going to be in its on state. Okay. So, this delay means here up to this point, let us say alpha is at 90 degree. Okay. So, here when alpha is equal to 90 degree, only then firing is going to take place. Firing is going to take place means the gate is connected to the thyristor, it supplies the pulse and the thyristor goes on. When the thyristor switch is on, you are going to get the source, that is the input will be available at the output. Source is connected to the load. So, now what will happen? At 90 degree you are going to get the output signal here. Okay. Similarly, let us assume this load to be a purely resistive load. So, voltage and current are in phase. So, the current value is a smaller amplitude when compared to the amplitude of the voltage. So, exactly when alpha is equal to 90 degree, you are going to get the output voltage. After 90 degree, you will be getting the output voltage. Now, when voltage you are going to get across the thyristor, that is during its off state, when thyristor is not turned on, whatever input is there will be available at the output. But when it is in the on state, voltage drop is around some 0.7 or 0.8 volts. So, we can take that in the waveform and show that on state, when the thyristor is on, it is showing 0.7 voltage. So, this part is when it is in the off state, when it is in the on state it is showing 0.7 voltage drop, and during the negative half cycle no control over the thyristor. So, automatically it is in the off state, so it follows the input. Similarly, for the next duration still it is in the off state till where? Till alpha 90 degree pulse is being applied. Once this pulse is applied, you are going to connect the thyristor as the on state, and once it is in the on state, what happens? The load is available. So, the load is available after 90 degree here. What about the thyristor? When the output is available, thyristor is in the on state. So, on state means you should draw a straight line. Means the on state voltage drop of a thyristor is around 0.7 to 0.8 volts. Okay. So, now what happens here during this condition? Again next state it will continue. Followed. So, this is how at alpha is equal, for some optimum value of the R2 resistor, exactly at 90 degree we are going to turn on the thyristor, in turn we are going to have a output voltage. Okay. Now, when the value of, we have to consider all the three cases, we will consider the first one. R2 is large, R2 is optimum and R2 is very small. When the value of R2 is very small, what happens? Large current flows through it, because we know that they are inversely proportional. So, when the value of R is very small, high current flows. So, high current flows means what happens? Already threshold is given. The peak value, before reaching the peak value itself, it is going to reach the threshold value. Okay. So, in this condition what will happen? In this condition, before the VGP peak value is achieved, before 90 degree itself it is going to turn on. So, at this point somewhere at around 15 degree, let us say the alpha is 15 degree and it turns on. Followed. So, now what happens? We are going to get a large output value. Okay. So, now alpha is equal to say 15 degree, we are going to get the output voltage. When you are going to get the output voltage, what happens to the thyristor? Only when thyristor is in the on state, you are going to get the output voltage. Similarly, when you are going to get the output voltage, thyristor in its on state will be around 0.7 or 0.8 volt. So, you are drawing a straight line. When the thyristor is in the off state, follows the input. So, follows the input. This is how the waveforms arise. The same thing while doing your lab sessions also, you will be finding out how these, you can step by step see at each point how you are going to get the different waveforms. Hope it is clear now. Now, which are the three different conditions now? In this case, what has happened? the value of the peak gate voltage is very less than the value of the threshold voltage. Okay, R2 is large is one condition. The other condition is the peak gate voltage that you are generating from this circuit, that is very less compared to the threshold voltage. Since it is very less compared to the threshold voltage, there is no possibility of turning on itself. So, you will not be getting any output across the load. Okay. Now, whatever is there at the input will be applied, just been reflected in the thyristor. Similarly, in this condition what happens? When the value of the peak is just equal to the value of the threshold voltage specified by the gate, at this instant of time what happens? Exactly at alpha is equal to 90 degree, the device is going to go to its on state. Okay. Next, in this condition what happens? The value of VGT, the value of VGT is very much greater than VGT. The gate pulse what you have generated, the value is very high when compared to the threshold voltage. So, what happens? Before reaching its peak itself, the value is going to get turned on. So, in this condition what happens? Before 90 degree, the firing angle before 90 degree itself, it is going to get turned on. So, alpha will always be less than 90 degree. So, out of these three waveforms, what is our observation regarding this resistance triggering circuit is, we can vary the value of alpha varying from 0 to 90 degree. You can vary the alpha greater than 0, less than or equal to 90 degree. So, whenever in any of the circuits when you are designing, you want to turn on the thyristors within this range of firing circuit, you can easily make use of this type of resistance triggering circuit method. So, the next method is the RC triggering method. Previously, we used only the resistors and we generated the triggering pulses for turning on the thyristor. In this method, we will see that we are by using resistor and capacitor combination, we will turn on the thyristor. Okay. Now, whenever we know that whenever we have an R and C along with the AC supply, always the voltage across the capacitor lags by an angle of 90 degree with respect to the voltage across the resistor. So, keeping this as the main concept, now what happens here? The different devices which we are using here, R1 is a variable resistor which is used to vary the duration of pulses, and D2 is the diode. See the direction of the diode, cathode to anode. Okay, so what happens in case of the diode is it helps in the capacitor to get charged. Okay. Now, D1 is the diode which allows only positive signals to flow through the gate, because negative signals should not be applied across the gate terminal. Hence, to ensure that only the positive signal is flowing here, we use D1 diode. Okay. So, now coming to the operation, let us see that during the negative half cycle, how the working takes place. Negative half cycle flows, negative means here we are also getting a negative value of voltage applied here, negative positive is the voltage applied here. So, because of the negativity here, this diode D2 which is in this position, cathode to anode position, this provides the path for the flow of current. So, here during negative charges D2 charges and this capacitor starts charging in the reverse direction. See the direction of the capacitor plates minus plus, because it is a negative current flowing here. So, till the negative half cycle is flowing in the circuit, the D2 diode helps in the capacitor to get charged. Okay. Now what happens? Alternately, since it is a sinusoidal waveform, alternately 0 to 180 degree positive, 180 to 360 negative cycle keeps on changing. Now what happens during the positive cycle? Positive cycle means what will happen? Here it will be plus and this will be minus. So when it is positive and cathode, D2 goes to the reverse bias condition. So D2 is not functioning now. So the current flows through this resistor R1. Okay. Along with this current, what happens to the capacitor? Capacitor is a storage of energy device, energy storing device. So what happens in case of capacitor? This capacitor, whatever the charges that have been accumulated on the plates of the capacitor, now it has to discharge. Okay. So when it is discharging, what will happen? When the capacitor starts discharging, the sign reversal of polarity takes place. When it was charging, it was minus to plus. Now the capacitor changes, that is reversal of polarity takes place, plus to minus, and it starts discharging. How does a capacitor discharge? Only through this path. So this path is used for the discharging and positive voltage. So here you can see diode D1 is present. Because of this, the diode D1 forward biases and then it allows the gate pulse to the thyristor. This turns on the thyristor. This is a general working of the RC triggering circuit. Okay. Now coming to the different values here, let us consider the value of R to be very large. Okay. If the value of the resistance is very large, what happens to the current flow? Current flow is very small. Okay. Since the value of the current is very small, what happens? The time taken to charge the capacitor is also more. Okay. So now what happens? The charging of capacitor takes place through D2. Now coming back to this waveform, let us understand that because we have connected R and C together with respect to an sinusoidal AC signal, alternating signal, always the behavior of resistor and capacitor in an AC circuit is that the voltage across the capacitor is always lagging by an angle of 90 degree. So what happens? Before you start the signal at 0, before 90 degree itself the capacitor would have started its process. Okay, that is in the negative half cycle diode D2 is being allowing the flow of current and allowing the capacitor to get charged in the negative half cycle. So with the help of this diode D2, the capacitor charges to the maximum minus Vm. This is minus Vm and this is plus Vm. Peak to peak voltage. So up to the maximum negative peak voltage the capacitor charges. Okay. Now what happens? After it is going back to the next cycle, has to start, a positive cycle has to start. So what happens when the reversal of polarity takes place, that is a minus to plus, the waveform goes for a positive half cycle, then what happens? This capacitor reverses its polarity and it moves towards the positive value. So from the negative value capacitor voltage, the blue line indicates the capacitor voltage, it is moving towards the positive value. Till where you have to give the you have to check for the value is till the threshold value of the gate signal. So threshold VGT will be specified by the manufacturer when you are purchasing the thyristor. So he will specify what should be the threshold voltage. Threshold voltage means it is the minimum voltage for which pulse the gate will apply or the gate will turn on the thyristor. So whenever you are designing a circuit, you should take care that the signal what you are applying across the gate to cathode must reach the threshold voltage. Okay. So now till where, because the value of R is large, the time taken will be very slow. Okay. So the time taken for discharging will be very slow, hence at somewhere after 90 degree it is going to turn on. So corresponding when it touches the voltage across the capacitor touches the threshold value, automatically we have seen in the previous one also, it goes and gives the firing pulses. Once the firing pulse is obtained, what happens? The switch is closed, device is turned on, we are going to get the load voltage. Means source is connected to the load by using the thyristor as a switch. So now what happens here, the output voltage is obtained only at this point. Okay, so a small value of output voltage is obtained. Okay. So, this is the value of output voltage. So, this angle from 0 till this angle, see it is cross 90 degree maximum value, this is known as the alpha, delay angle, firing angle. Okay. From alpha to pi you are going to get the output voltage. Again pi to 2 pi there will not be any output voltage and this continues. Now, let us see the waveform for the thyristor. Okay. We know that already when the thyristor is in the on state, it has a voltage drop of 0.7. So, 0.7, when you are going to get output voltage is 0.7. So, you will get something like this. Okay. In the negative half cycle, this is conduction time. When it is conduction time, 0.7 is the on state voltage drop of the thyristor. So, we are representing it as a straight line, and in the negative half cycle again we are not going to get any output voltage. So, what we are going to do? We are going to take the negative half cycle. Similarly, this keeps on repeating. So, you might have understood the difference of how you have to draw the output voltage and how you have to draw the thyristor voltage. Now, the next case, when the value of R to R is very small, means what happens? Resistance is small means there will be a high current flowing, inversely proportional. So, when the value of the resistance is small, then what happens? Current is high. Current is high means quick charging and discharging takes place. So, what happens? Before it reaches 90 degree itself, you are going to turn on. That is, the value, the capacitor is discharging at a fast rate. Okay. So, the threshold voltage is obtained much before the reaching its peak amplitude. So, here in this case what happens? Here itself the thyristor is going to turn on. Thyristor is going to turn on means you are going to get the load voltage. So, load voltage will be like this. Okay. Maximum value of output voltage. Now, here thyristor voltage, how we have to draw? When the load voltage is available, thyristor is in the on state. So, for this entire duration of time, you are going to get a straight line, and the thyristor follows the input only for some duration of time. So, this is your alpha. Okay, 0, alpha up to pi it is conducting. From pi to 2 pi it does not conduct. So, it follows the input. So, this is how the waveform of the thyristor lies. Okay. Now, you can observe from these two waveforms such that when the value of alpha, let us say alpha is more here, when the value of alpha is more, when alpha is high, what happens to the output voltage? Output voltage is less. And when the value of alpha is small, output voltage is more. Okay. So, when the value of alpha is small, you are going to get a larger output. So, using the same method of controlling, you can either vary the speed control, you can vary the illumination control of lights. Like this, for different application where you are going to use this type of triggering method, you can make use of RC triggering circuit. Okay. One more thing is, compared to the previous one, resistance triggering method, the alpha which we could use, a firing angle which we could vary was from 0 to 90 degree. This was the limitation if you are using only the resistance type of triggering circuit. Now, in this case, what do you observe? You can observe that from 0 up to 180 degree, depending on the value of R, the variable value of the resistor, depending on that value of R, you can vary this firing angle by using RC triggering method from 0 up to 180 degree. So, this is a speciality of using RC triggering circuit when compared to R triggering. R triggering only 0 to 90 degree you can provide the firing pulses. Okay. If you are using RC triggering circuit, you can provide the pulses from 0 up to 180 degree. Okay. So, this is the advantage of using RC triggering method. Now, in advancement to this, if you want to use a full wave, Now see here, you are going to waste the negative half cycle. Instead of wasting this negative half cycle, you can also, this is only for half wave, one half wave of the input waveform you are achieving control. If you want to do it in case of a full wave, the circuit is as follows. In the RC triggering circuit, the previous circuit which we saw was only controlling a half wave. Now if we want to control both half wave as well as full wave, then we have to use this circuit. This is a full wave bridge rectifier circuit, where AC you will be getting the output voltage available here will be a AC to DC converted output voltage. Because we are using 4 diodes, what happens? 2 diodes in anti-parallel will conduct at the one instant of time. D1, D2 in the positive half cycle, you will get a positive load. D3, D4 in the negative half cycle, again you will get a positive half cycle load. So here what happens in this case? Positive, negative, all are being converted into a DC output voltage, all are positive output voltage. So this VDC, the same thing, this will be the input now. So instead of wasting the negative half cycle, if you want to make use of both positive and negative half cycle, just insert a bridge rectifier, diode bridge rectifier here. So the operation will be the same. Okay, depending on the value of R. Here the value of R is more, so the charging time taken will be more. What happens here? The pulse is generated somewhere here. Okay, so 0 to alpha, this is the pulse duration, alpha to pi, you will get the output voltage. Corresponding thyristor voltage you can draw. Okay, similarly when the value of R is small, what happens? Instead of charging or discharging for a longer duration, you will achieve it quickly. The alpha will be achieved much before. Okay, so this is how you, here also you are going to control 0 to 180 degree itself. Okay, but without wasting, power loss also plays an important part while designing the circuits. So when you want to save the negative half cycle, or you should not waste the negative half cycle, you can convert this. This is a full wave type of RC triggering circuit. So this two methods what we have studied, R triggering, RC triggering. R triggering controls 0 to 90 degree firing angle that can be generated, and in case of RC triggering you can generate firing pulses from 0 to 180 degree. Next type is the UJT type of triggering method. In that we can control from 0 to 360 degree depending on the application where we are going to use such type of circuit. So in detail about the UJT, what is a UJT, how it behaves, how it is in the on state, what are its characteristics, we will be discussing in the next class. Thank you.